All right. I'd like to share the path I've taken to get to where I'm going to talk to you about today. So I'm going to share with you a path to a cleaner world with abundant energy. The journey I've got is I started the first 20 years of my career working in automotive. Worked on the EV1 as my first vehicle program. It was the first commercial vehicle to get more than 100 miles of range, which was actually very good when it came out. And my last vehicle program was a Chevy Volt, which was the first commercial high-volume plug-in hybrid. And obviously working on these, there's two things you're always after, which is you want to improve efficiency, you want to decrease emissions. After that, I spent about 10 years working on scientific software, engineering software, and got a chance to work with OEMs globally, from everything from electronics to aerospace. And the same themes show up, which is you're trying to increase performance of the design, you're trying to decrease the environmental impact it has, and most importantly, you're trying to decrease the time to get to market. Well, the key problem with all these industries and things that we do is energy. And it's where do I get the energy I need to do the job the way I'd like to do it? Where do I get the clean energy so I'm not having an impact that goes beyond what I'm trying to deliver as a service? And I personally like the prosperity that energy brings. We actually have a very rich country in terms of energy for the individuals here. And I like a clean world. I actually had a chance to drive through some LA smog when I was younger. And it's very hard to communicate how bad the smog is unless you've ever gone through it once or twice. So clean energy is really important. Now, 4 years ago, I had a friend that I'd known for a while recruited me to join him in his efforts on making clean energy and abundant energy. 2 years ago, I convinced myself this could be done, and I went full-time on doing this. And what I'd like to do today is, by the time I'm done talking, I'd like you to understand that even though it's really tough to wirelessly charge your phone from just a few millimeters away, it's completely feasible and economic to power civilization from 37,000 kilometers away in orbit. So, we're going to talk about expanding the electric grid into orbit, but I'm going to start with a bit of history. If you can flip the slide, or do I have the remote here? Is this it? Yep. All right. Maybe. Is it on? There we go. Well, you see my slide in my next slide there. I'm sure you'll get that taken care of. So the slide you did see, that's showing you the complexity of the electric grid in the U.S. So the U.S. produces about, I think electricity is about 20% of the global energy. The U.S. is a large fraction of that. With the total electricity that we produce, we have about 11,000 power plants. And there's, depending on how you measure it, there's about 1 million kilometers of electrical lines that tie everything together. In the U.S., we're very energy rich. We have on the order of about 1.5 kilowatts per person in terms of the energy that we have available through electricity. That 1.5 kilowatts, about 40% of that's for powering our homes. The rest is for everything else around us, street lights, industry, etc. Now, the disparity is, if you look at this globally, the average globally is about 350 watts per person. And if you go even further and you look at this, about 13% of the world doesn't even have access to electricity. And these numbers have been improving wildly. From 10 years ago, this number was much higher. But energy and electricity is very important to the prosperity we're going to have. Now, for a long time, the energy grid was actually very simple. You had consumers that would say, I need to have energy available. You had utility scale generation, and as the demand went up, the power that was available went up. It was a just-in-time sort of delivery system. And while electricity itself is fungible, it needs to be made available when and where you're asking for it. And that leads to the need for the massive transmission systems, the massive distribution that we have. Now, starting in the 1970s, solar started being put onto homes as a way to get clean energy into the houses to decrease energy costs. And in 1979, the first commercial net metering got put in place. This became the origins of our first distributed generation in the grid. So it's actually been growing for a long time that we've been making the grid more complex and bringing things in. And as time goes on, we've had a significant increase from these first tens of watts or tens of kilowatts that were available to now a significant fraction of the grid being powered by renewables. And it's growing each year. What that has happened now is it means as we grow renewables, these tend to be very transient in nature, and that means we have less firm power generation that's out there. And we talk about this is what it means to have transient power. This is some power that, this is the graphing of the capacity factors for electricity generation in Europe. Gentleman has done a fantastic job of taking the public data, tying it together. And what you see here is you see the line on the top shows you how the capacity capability, or the installed nameplate capacity for Germany's solar has grown over the years. The graph at the bottom showing you what fraction of that's actually delivering power. And the problem we have in the Northern Hemisphere, in the U.S. is very blessed because we have the Southwest, which gets a lot of energy, but as you start working your way up to the Northeast, into the upper Midwest, we have similar problems to Germany and the UK, in that solar has very, very low capacity factors on average. We have clouds, we have seasonal variation, all of these things combine to make the ability to pull the energy out of the system very low. You see with Germany, they're getting down to 1 to 2% in the dead of winter. So I install a megawatt, I get 10 kilowatts of power out. That's very, very tough. It also makes it tough to balance a network out over time. It means as I give preference to solar coming in, because once I build it, it's free. I mean, at the end of the day, it's a capital expense. There's no real O&M expenses that go with it that are that large. So if it's able to run, it can bid any price to get into the grid. And it actually slowly pulls down the capacity factor of the firm energy sources that are out there. Now, the way that we're trying to address bringing this power in, balancing the network out, is start putting utility scale storage out there. In 2012, the best I can find, this is the first example of utility scale solar being installed. But as you start increasing the amount of utility scale solar you put in, you start running into a problem, which is you start pulling your firm capacity out. Your firm capacity is not able to track. It doesn't make economic sense for it to even try to track very high variations between renewables and firm. And you have to put larger and larger amounts of batteries in to deal with it. So this is from the European Association for the Storage of Energy. They put their tipping point for the grid at about 60% transient renewables. You have to start putting in exponentially more storage into the grid. So if you take a look here, you can see the duration in hours is actually a logarithmic scale there. So as I go to higher and higher levels, there's a wide band. It depends on the specifics of your electric grid, but you got to put more and more, and somewhere around 50 to 60%, you reach a tipping point. You're just spending your money on storage. And at the end of the day, storage is not generation. So one of the approaches to solve this is start looking at distributed storage. So the rollout of EVs means that you've got potentially storage in the EVs that can be taken advantage of. There's things like power walls that are available to consumers to try to cost level. And this in turn gives us some more knobs to twist to crank the efficiency of the grid up a little bit to deal with these transient sources. And these changes are going to only increase. This is from the White House's long-term energy strategy that was just published. And this is their intention for how the energy in the U.S. is supposed to change. And so all the things that we've seen come in have come in because we're simply trying to get rid of a little bit of the CO2. Getting rid of the rest of it is going to drive even bigger changes. So the path that we're following right now to a cleaner world is solar farms, wind farms, grid storage, transmission lines, distribution lines, demand management. And the question to ask is, what does this require? Well, first off, it's going to take a lot of minerals, lots and lots of scarce minerals. These are charts for mineral consumption that were put together by the IEA. And you can see as they go from today to 2040, under some of the scenarios they've looked at, we're looking at dramatic increases in the amount of minerals that have to be mined, processed, and brought into use in order to basically keep what we've got and live the same way with the replacement of renewables. Second one is we need land, lots and lots of land. This is from, I think this was IEA. Yeah, this was an NREL report. And with this, they looked at what does it take just to make the electric grid green by 2035. This is a great chart, but if you look at it, you can see we're taking several states worth of land need to be dedicated in one way or another to energy generation and energy transmission. Wind is generally put into the category of I can get dual use out of it, but it's primarily only going to be useful for farming and things like that. So roughly we're looking at 4 states worth of land are dedicated to energy generation on top of what we already have today. Now the reason for this is that we have to move the energy from where we can harvest it efficiently to where people are actually using it. So that in turn is going to drive lots and lots of wires. Rough estimate from BNEF is that we're looking at like $21 trillion in global grid upgrades. And actually, depending on the week that I look, the numbers keep creeping up. I think I've seen one now, which is 23 trillion. So we've got trillions of dollars that are looking to be spent just on wires to move energy from where it's produced to where people need it. If you try to make solar in the wrong locations, like you try to make solar in Michigan, you're looking at massive overbuild. You try to collect wind where it doesn't really make sense, you're looking at massive overbuild again. So transmission lines are the way to balance that out. We're looking at doubling the size of the grid to approximately, depending on how you do it, and these numbers are all over the place. There's capacity, there's circuit wires, transmission systems, etc. But the BNEF number puts it about 152 million kilometers of wires need to be installed for a clean energy grid globally. That's enough wires to go to the sun. That's a huge, huge amount of wiring that needs to go in. So the question is, where can we get utility scale renewable energy that's always available? Because if we can do that, we can solve the problem of storage, we can solve the problem of transmission if we can deliver it where we need to in a useful way. Now, the thing that you can look at is a couple kilometers up over our head, get out of this Earth's shadow, you've got access to about 1,400 watts per meter squared constantly. So a satellite in orbit, if it's got the right orbit, can get almost continuously 1,400 watts per square meter. On the ground, depending on where you live, you've got access to between 50 to about 300 watts per meter squared as a daily average. The best spots on Earth, I think, will get up to about 500, but that's a real tough problem to harvest the energy you want, but it provides an opportunity. And the reasons for this is, if you look at it, when we have things in orbit, the Earth's atmosphere actually acts as a big filter. So it lets through the stuff that we can see, and you can see here from how the Earth blocks solar energy, and it lets through other radio waves and things like that. And the reason that we lose a large fraction of that energy from space is because we spend half our time in the Earth's shadow. The Earth rotates, we sit in its shadow, and depending on the weather where you live, the clouds are obscuring the access to the sun and reducing the amount of energy you get. So in space, a solar panel can produce power almost continuously. So here's the opportunity. And if you put the pieces together, what you end up with is I can take continuous solar. I can move it from solar to DC, just like I do in a solar farm on the ground. You can then take DC, convert it to RF. And we're surrounded by RF today. Every phone in here is producing RF. The wireless systems on your laptops are surrounding you with RF. We can focus it in such a way that we can get it to the ground very efficiently. We use a device called a rectenna. And what a rectenna is a much more efficient conversion from radio frequency to DC than a solar cell is from light to DC. And then we can plug it into the grid just like it's a solar farm or a wind farm or anything else. And that in turn provides us with a mechanism to be able to harvest this continuous energy and move it where it needs to be.
Just a quick question.
Sure.
How much efficiency do you lose at each of those conversion steps?
Great straight man. I'm going to show you a slide in just a minute. So just give me one more slide to get through. So when we do this, we're looking at beaming power at about 250 watts per square meter. So it comes in at a power level that doesn't affect the atmosphere. That's been looked at for a long time, and it's about a quarter of sunlight. I've actually been in beams that are about half this, and you can feel warmth, but it is a safe power level to bring in a controlled environment. This is higher than you would have for occupational exposure, but the systems that would be built would be keeping people and animals away from it. Now you asked the question, what is the efficiency? So this is kind of the walk-up of how you can convert power. So there's a lot of ways to compare it. We're going to compare just on a square meter basis. Usually on the ground, we're going to start with half the power is lost to night. We're going to lose another fraction to atmosphere. We're actually, because of commercial reasons, you're going to use about 20% efficient solar cells. And by the time it's all said and done, you're getting up to maybe 5% of the solar energy that comes in, you're able to put into the grid. The usual question is, now I'm putting microwaves and all these efficiency chains in place. What makes sense, what doesn't? Well, the first thing we start with is we're going to start with about probably a 40% efficient solar cell. So there's actually space-rated cells that are above 40% right now. We can talk about economics as another discussion, but there's ways to make this an economical approach. And then we've got a series of conversions. DC to RF, you're looking at about 85% efficiency. Demonstrated stuff right now is seeing about 75%, so there's some range to go there. Atmospheric's going to attenuate, depending on the weather, a few percent. The beam coupling is a bit that most people usually have questions on. And what's really surprising is, depending on the size you make your transmitter and receiver, we can actually move the beam with almost 100% efficiency. And then finally, on the ground, RF to DC, we have lab stuff right now that's getting 85%. So there's some scaling that needs to go on with that. And then finally, it converts just like you convert DC to AC. You get to ground. Net results, you're looking at like 27% or so efficiency moving through the system. And to kind of put it in mind what we're looking at here, if I look at mined uranium has about half a megajoule per kilogram. So if I go say I'm going to make energy by digging stuff out of the ground and doing something with it, the highest energy concentration I can pick up is uranium. And I have to do processing and everything else to make that a lot more energy dense to put it into a reactor. But if you look at the energy density that people are talking about for space-based solar, what's kind of surprising is it's comparable to uranium. Actually, it's better. I put this out as a challenge a couple months back and said, prove to me I'm wrong. And the numbers that we get say that you're manufacturing something which over its lifetime can produce as much energy as you're going to get by mining uranium. It's just a matter of assembling things in the right way and putting it in the right location. That's a really, really powerful energy source right there. We just have to build it right and put it in the right location. And that gets us to a future where space-based utility scale generation be connected to the grid. Now, what I'd like to do is give you a short history and go into more details on how this comes together. This is actually more than a 100-year-old idea. The father of the rocket equation, Konstantin Chayefsky, he said, hey, you could do something in orbit, we could get energy down on the ground. Very vague, but kind of thought through the idea. Isaac Asimov introduced the idea in 1941 with the short story Reason, and had it set where they were beaming microwave power back to Earth. 1968, Peter Glaser got the first patent for space-based solar, and it actually kicked off almost more than a decade of work that happened at NASA and DOE looking at trying to make this a reality. And during that time, they demonstrated the physics, they demonstrated a lot of the technology that wasn't quite ready for prime time, and they did hard analyses on the economics. That culminated in 1980 in a NASA DOE study. It's thousands of pages, it's actually publicly available, and it explains how they looked at solving the problem, what the challenges were, and eventually the capstone on that was, we're not going to do it yet. But there were things that were hidden there that made it interesting, such as the fact that they said in about 40 years it might make sense. Well, it's been more than 40 years. And in 2023, Caltech actually got a demo from a donor for $100 million for them to put something in orbit that would help accelerate space-based solar. And they've demonstrated the basic components, a system and a design that could potentially deliver it. And they're not the only people working on it now. To help you understand what was originally proposed, and maybe one of the reasons it had such a hard time making it beyond the proposal stage, is the first engineering study that went on in prior to the 1980s. They spent about $80 million in today's dollars. That's a lot of money to spend on a conceptual engineering project. It was coming off the back end of the heady days of the Apollo program. The 1979 Boeing and NASA space-based solar proposal, they actually proposed building 60 satellites that were 20 kilometers by 5 kilometers by half a kilometer. Okay, that's hard to conceptualize. So we actually took that and put that over top of Manhattan here. So the little squiggly stuff you see on the bottom is Manhattan. This is how big that satellite would have been, and they were proposing to build 60 of them. And oh, by the way, they weren't just going to build those. They were going to build a launch system. They were going to put men in orbit. They were going to put men in LEO, men in GEO. And the system they had would literally have each satellite getting something fixed every 2 hours because of the reliability of the parts that they were proposing. And this is all written up. Zooming in a little bit, the antenna alone that they were proposing to transmit the power was 1 kilometer across. And you can see the Manhattan skyline there compared to a 1 kilometer across antenna. So in 50 years since this idea first came together, advances in electronics, manufacturing, automation, All these things make it possible for us to look at making something much, much smaller. This is a minimum value proposition satellite that we're proposing right over here on the right. So we're actually looking as a first step towards having something which is commercially viable being smaller than the antenna that was proposed in 1980. Now, we've also had 50 years of design concepts from Peter Glazier's first proposal in '68 on through the NASA DOE proposals and a whole bunch of ways to solve problems. So the initial systems were limited by using things like klystrons for powering stuff that in turn drove structures, that in turn drove all these other engineering decisions that need to be made. Initially, it wasn't possible to even consider having telerobotics or automation put things together. The controls that you need weren't available. You're talking about, like we talked about earlier, the electronics were equivalent to your key fob for being able to control it. So we've had all these things happen, plus we have higher volume manufacturing. Solar cells have almost tripled in efficiency since this concept first came together, and that's enabled different concepts to come about. And it's even enabled different ways of thinking about how to do it. The initial concepts were to put something in geosynchronous orbit. Okay, geosynchronous orbit's like the highest value real estate in space. And there's different orbits you can choose, but you have to basically negotiate to get those orbits. And so there's other things that can be used to go after there. So the question is, why bring this back, dust off the old reports, and look at it? Why now? What's really changed? Well, we have to thank SpaceX for doing some absolutely amazing things. This is from the Visual Capitalist. This is a progression of space launch costs. In the past couple of years, we've had launch costs collapse. And Falcon and now Starship coming online are driving those costs down, that we're looking at sub $1,000 per kilogram to put stuff in orbit. We're looking at highly reliable launch systems that have got a pedigree of putting stuff in orbit literally weekly. I think they're at right now with SpaceX. And Musk even says he can get to $10 a kilogram. Now, he's not the only guy that says stuff can be put into orbit for $10 a kilogram. There's at least 3 other alternative launch technologies that are out there. Spin launch, long shot, and I never get these guys right. It's like wave power or something like that. That they're all looking at alternative technologies that can also achieve in the $10 to $15 per kilogram range. So the access to LEO, that cost is coming way down. That has massive implications for what we can do. In fact, if we look at launch capability, this is a graph of all the launches that have occurred since since the beginning of the launches, the space program. And you can see we've summed up the annual payload. So you can see we had massive growth from 1960 to 1970 with the space race. And then after Apollo spun down, we've had almost 40 years of the same amount of junk goes up every year. But starting in 2020, all of a sudden the tonnage that was being put into orbit took a dramatic leap forward. And to show you the types of material we're putting in orbit, if you look here, the right side there has a bunch of different systems that have gone up with the tonnage that goes with it. So the Hubble telescope's like 11 tons. The Mir space station was about 130 tons. Starlink is a system through July 2023. I have to read the number carefully, is 1,500 tons of material put into orbit. I mean, this is an absolutely astounding change in the scale of what we're putting into orbit. In addition to the launch capacities going up, we're also looking at the density, the kilowatts per kilogram that's possible in space going way up. So in other words, for each pound I put up, I can potentially generate a lot more energy than I could just a few years ago. Going through all of the published studies that could be found starting in '74, plotted out here the power density, the watts per kilogram for the different concepts that have been proposed from NASA, from Europe, from Japan. And starting about 2015, there was a massive upkick in what was even possible in a paper study. And we've gone from about the order of about 250 watts per kilogram to right now the best guys think they can hit about 2,500 watts per kilogram of something they put into orbit. So we've got launch costs coming down, launch capability going up, and we've got the amount of power we can get per kilogram going way up. And the final piece is the problem that NASA ran into is when they proposed putting up space-based solar as a national solution in 1980. They said we need $1 trillion in today's dollars and 25 years, and we'll get the first watt on the ground. And that first concept they had required putting something in the order of 100,000 tons into orbit just to be able to turn the system on. Okay, that's a problem. 25 years is a problem. Nobody can make an investment that's more than a generation. So, bold vision. Have to tremendously applaud the vision the guys had, the boldness to propose it, but it died in the crib. If we look today, the minimum mass that's required to launch for somebody to be able to turn power on is orders of magnitude less than it was in 1980. So this is the other key part. This drops the total investment that's required to be able to turn on and get the first watt on the ground, get revenue, and start a virtuous cycle of reinvesting that revenue into producing more power. And let's do my little play.
Commercial reusable space launch. Moore's law and modern
what we're proposing here.
Enables in-space infrastructure. Space-based solar power satellites are the key infrastructure for expanding into space. Low Earth orbit is not suitable for solar power satellites, but on-orbit propellant transfer allows access to higher orbits at low marginal cost. Virtus Solis's power satellite constellation is planned for a 12-hour medium Earth orbit called Molnia, which is uncrowded and highly elliptical, spending 11.5 hours of every 12 at 35,000 kilometers above the northern or southern hemisphere. This orbit allows 2 ground stations on opposing sides of the planet to be served sequentially, providing baseload capabilities. The arrays of thin tile satellites are assembled in the final orbit, transported flat-packed in racks for maximum usage of the rocket's payload bays. The assembly robots extract 25,000 satellites and then assemble them into arrays of 100,000 or more. Each autonomous satellite delivers about 1 kilowatt to the ground, and the arrays can scale up to over 20 gigawatts each. As the satellites are interchangeable and cost less than a laptop, servicing amounts to removing and replacing elements of the array. The assembly process is simple. Extract the satellites from the racks and click together like Legos into large circular transmitters of 0.5 to 3 kilometers in diameter. Once a sufficient size, the arrays can transmit power to 1 or more ground stations, and a constellation of 2 or more can provide baseload power to multiple ground stations simultaneously. You can see this constellation of 3 power satellites provides redundant coverage to nearly the entire northern hemisphere. The ground stations are 2 kilometers in diameter and can absorb up to 1.5 gigawatts each, powering 150,000 people, and can be sited and built like conventional solar farms near end users. The launch vehicle can return to the launch site and be reused with only small propellant use. Virtus Solis is Latin for the power of the sun. Virtus is the root of virtue, and as the Romans didn't have a concept of energy as we do, it is better translated as power or kingly authority. This power to change the world aligns with our vision of clean, firm, low-cost, globally available energy. Low-cost energy is the greatest lever for universal prosperity.
All right, so that's how we're looking to put our system together. You've seen some of the rationale on how we think the trends have changed to make it possible. The key part, and this is where I think a lot of people have no experience as to, is this even possible, comes down to power beaming. So I'd like to start with the last 15 minutes I've got here going through power beaming, and I'll actually show you a demo of it actually working here in the lab, everything permitting. So power beaming is the key. This is what Peter Glazier was doing his work on in the 1960s. Dr. Brown at JPL actually demonstrated power beaming across a kilometer using part of the Deep Space Network. So this has been a demonstrated technology. These are analyses here that came from the NASA concepts in 1980, and they were looking at what efficiency they could achieve with that 1 kilometer dish operating about 2.5 gigahertz, pushing energy down to the ground. And their conclusion was they can get north of 80%. And by things that we can do now, we can get north of 90%. 95% is the target we're actually shooting for. So power beaming's been looked at, it's been understood for 50 years, it's just it doesn't make sense to do it on the ground. And the key reason for this is that you need aperture. I'll do an example here is like, everybody looks at lasers, and you see a laser and it's like, I'm able to keep a very, very tight dot with a laser. And the reason is because this is coherent light, it's organized in a particular way, and then when it spreads, it still spreads at like a 1 over R, but because it's such a tight beam, it has just a few degrees or tenths of a degree of spread, it's able to concentrate the energy. Well, electromagnetics is electromagnetics, whether I'm working at 10 hertz, a terahertz, or a gigahertz. And what we can do with a laser, we can reproduce electronically with microwaves with RF energy, but we need aperture. It has to be big. So trying to do wireless power transfer between mountaintops, you've got to trade off between how big am I making the aperture, what power am I working at, how safe is that going to be? Coming from overhead to down on the ground, we build solar farms that are kilometers across already. We already are building things that are on the scale that we need to make terrestrial receivers. And in fact, a reasonable terrestrial receiver for something working at about 10 gigahertz only needs to be about 2 kilometers. So a 2 kilometer across receiver is actually smaller than many of the solar fields that we're now installing at utility scale. And if we can build a big enough structure in space, that's the last piece we have to get through. We're already building things that are on tens of meters. The technology's there to start getting it bigger, and there's actually government contracts to start putting large-scale antennas and manufacture them in orbit. So there's a whole industry spinning up to be able to build bigger and bigger structures in orbit. But this is the key. We can make a large, thin aperture. At the end of the day, the pieces we're looking at here are very thin. I mean, this is a 2.5 gigahertz antenna. All I need is a piece of copper. I need another piece of copper and something to separate them, and I can transmit RF energy. I need thin film electronics to drive it, and conversion of solar to DC is thin film. So devices that are a few millimeters thick can basically provide all the functional behavior that we need to convert solar energy into RF and manage it. And the management problem doesn't require supercomputers. This is something that's a combination of analog hardware and low-end microprocessors. Yes?
So is there a worry at all that this beam like hits a plane that's flying through the stratosphere or something?
Yeah, there's birds, there's planes, there's guys that are using light aircraft, gliders, and things like that that all potentially intersect the beam. Right now, we don't believe there's any interaction that's going to be a serious concern. These will be restricted areas. If a plane was wandering in, or we have any other kind of an intrusion, these beams can be shut off in, I forget the time, but it's like less than a second. You can shut the entire thing down and then bring it back up when you need to. And the baseline plan is to have some local energy storage so that the power delivered to the grid will stay pretty constant.
In order to get a 2 kilometer receiver on the ground, what's the diameter of the transmitter?
Right now, the most efficient match of areas is for the two to be the same. So the roadmap we're following is actually starting with something on the order of a couple hundred meters across as initial demos, which will have lower efficiency, and then keep adding parts to it to reach about 2 kilometers. So 2 kilometers in orbit and 2 kilometers on the ground get us a very efficient match.
Do you have concerns about space weather and solar flares interrupting or damaging the electronics up there?
Yeah, but I mean, there's already a long experience of being able to keep solar cells working in orbit on spacecraft. I think the longest running spacecraft right now is like 35 years. And I mean, we've been knowing how to put solar cells up for a long time to make it work. There are things like degradation from radiation. You've got different choices on that. You can shield it. That will make it last longer. There's actually self-annealing solar cells now that will recover from the radiation damage if you cycle them properly. So there's design decisions to be made on how you're going to approach the problem. You can either let it wear out. You can make things that heal and will last longer. You can look at a replacement schedule. And by the way, you'll also get damage from micrometeorites and other junk in orbit. But you're looking at a highly redundant parallel system that losing one element in the array will have very small impact on the system. And then depending on the architecture, we've chosen one we can actually service them as an operations and management. We can go pop pieces out and put pieces back in to fix it.
There's a couple of questions online. I think actually you just addressed one, though. It was concern about space junk.
Yes.
Yeah. The other question, though, is how much more efficient would 2 kilometers of receiver and beamed solar be versus just having a 2-kilometer solar farm?
The rough numbers we use is that we get about, the economic one we use for back of the envelope is we're about twice the cost of equivalent energy, or equivalent area, but 6 times the energy received. So we're about 3 times better than doing something equivalent on the ground. All right? So this is the key of it right here is we go through the atmosphere, we can work at very large apertures, and actually right now we're in the middle of an effort with the University of Bristol to put a tool out there that's available to government, academia, and industry to be able to simulate 1 billion or more antennas. And the reason for this is so there is a standard platform, because this is something that hasn't been built before, that everybody from regulators to academics to those of us working in the field have got something that we can simulate this on and see what happens that goes through the atmosphere, what the beam patterns will be like on the ground. And we think that's going to help spur this entire thing on. So Dr. Timothy Pelham is actually leading this effort at University of Bristol, and we're supporting it right now from an industry. So I will put a plug in here if anybody's interested in being involved in that activity, antennas, etc. Please contact me, and we'll add you to the distribution list for the development. And like right now, we've got membership from Thales, Airbus, a couple of the software vendors, etc., that are helping out. So power beaming's been demonstrated since the 1970s, actually since the late 1960s. We've been following a path to get to commercial power. So roughly on this chart where the commercial power is at is probably about the smallest system you're going to be able to make that's going to put power on the ground that makes any sense economically. Our path has been, we started up within our first couple of months, we did our first demo, which is way down there in the lower left-hand corner. Our second demo pushed us further up, and our third demo we just did this year was a 100-meter demo with just shy of 100 watts of power being transferred. And we're working on a terrestrial demo that's further along and moving up towards an orbital demo once we complete our A-series funding. So show you a little more details as to what's there. There we go. This is effectively a proof of concept of what a satellite looks like. So we've got an array there of about 6,400 antennas. It's backed up by 100 amplifiers. And with that system, we're going to a couple of different targets. So we've got what's called a lectenna wall. It's not fully populated, but you can see the lights that are on there at the top. We've got a rectenna receiver, which is that cross you see, and then we have a thermal wall. If we just put the RF into some foam, we can see what the beams look like with an RF wall. And the chart you see in the middle, this is all the things that, as a good engineering team, you pretty much need to characterize to understand what wireless power does. So I won't bore you with the details on it, but this is what Paul Jaffe from the Naval Research Lab proposed as a consistent way to take a look at what everybody does across the industry. And when you fire it up, this is what you get. The particular array, we've got different modes we can operate it in. This is the simplest mode that moves the most power. And this is what a cross-section of the beam looks like based on our analysis tools and the validation that we did against it. And as we are able to get bigger areas, we improve the controls that we have, and we deepen the integration we have between all the parts. This beam will get tighter, and the efficiency that we're able to communicate out will go much better. And in fact, to show you how this works, I'm now going to show you 1% of our demo that we did in March. So what I have here is this is one of the rectenna panels that you see over on your right. That's one of our transmitters, and that's an amplifier on the back end driving it. And now let's see if everything works like it should. I'm now moving wireless power. And to kind of yeah. I'm going to tell you there was a lot of stress to make sure that actually worked. But to kind of show you that it's actually, this is wireless power, not something else going on. There's a beam here. As I move tinfoil through it, there's all the power being blocked. But the frequencies we're working at are able to go through, a lot of things that are more organic and like that. So here's a piece of paper, and I can wave paper around, no real impact on the power. The beam itself is actually quite tight. So let's see if I can get in here. So probe it, there we go. So you can see this is the edge of the beam. Yeah. I've spent hours in front of this thing. So it doesn't like me, it won't go through me. I can.
About any impact on you.
The power levels, the safety standards are, FCC has safety standards for what kind of RF levels you can deal with. There's basically 3 levels, which is I don't know that I'm being exposed to it. I'm a worker in an industrial setting, and I'm in an enclosed environment that people can't get access to. So like your microwave oven runs at, thousands of watts per square meter. That's how it heats up your coffee, melts your cheese, whatever. That's a secured environment. It can go to a very high level. There's other things where if I'm a worker, I can go to, it's about, I think it's 100 watts per square meter for a worker, or 10, I forget which. These things are operating well below what you can, this demo here is working about what your cell phone power level works at. So this is a low power demo. We actually go into a production system. What there will be is a secured area that people will not have access to. The peak power inside of it will be about 250 watts per square meter. So that's wireless power demo. And so we can actually do this. We can move power, we can focus it, we can steer it. The demos we did, we actually were steering this a couple degrees back and forth electronically, and those are all the core capabilities you need to be able to put together a satellite that's going to be able to move power.
Sorry, when you say steer, do you mean
Electronically. Yeah.
curve it or?
No. What you do is, these are phased arrays like phased array radars. So by changing the phase across the antennas that are there, you can take the beam from pointing straight to going to the left, going to the right. So one of the 2 capabilities you've got to have is one is you're going to have to be able to move power, which means I can transmit and I can rectify. So this piece of hardware up here receives the RF, rectifies it, and then makes it available to the LED. And then steering is critical because you're looking at things that you're about thousandths of a degree, better than a thousandth of a degree accuracy you need to have on getting this thing from orbit onto the ground. So you've got to have a way that you can accurately aim it, and you're not going to do it by tilting the satellite.
It uses a terrestrial transmission.
That's always the question that comes up, and people are like, I got all this energy that's trapped like in, somewhere up in southeast Washington state, and I can't get it to California where they'll pay me a premium. And the problem is, when you deal with the Earth, you've got curvature of the Earth. So if I try to move something terrestrially, we've tried to find a test site which is 100 kilometers. And 100 kilometers means I have to find the edge of one mountain, the edge of another mountain, and get over the curvature of the Earth. So curvature of the Earth means you've got to have repeaters repeatedly. The second one is the energy power density you're moving at. When I talk about moving a gigawatt of power at a utility scale through the pylons you see, you're looking at a fairly small area carrying tremendous amounts of energy. When you start looking to move that wirelessly, so people have proposed using lasers, there's people proposing using microwaves, the energy density becomes so high, you end up trying to put circuits around it to deal with it, like laser guard bands around a carrier laser or laser guard bands around a microwave is what's been proposed. But it's just simply the sheer problem is you got to repeat this like every 20 to 100 kilometers. And in fact, one of the pieces that was real fun to look at was, people say, well, couldn't I just bounce this up and then bounce this back down? There's actually proposals for doing like a global energy grid based on that idea. And we kind of look at it and go, well, if you're going to bounce energy up and bounce it down, why not just collect it above? So we see that for this utility scale power, this is about the only way to deal with it.
One other quick question. Do you get a loss in the transmission like you would get, for instance, corona loss in a high voltage transmission line? Oh, sorry. Yep, sorry. My question was, where does the loss in the transmission largely come from?
It's
compared to things like corona loss in a high voltage long line transmission.
Yeah, if you push microwaves too high a density, you will get that. People have looked at using microwave boosted launch, and the power levels are so much higher than what we're working at, but they've looked at using microwave boosted launch to try to get ISP up on rockets. And the problem is you hit the upper atmosphere, all of a sudden the microwaves just jump all over. The energy gets brought out as an arc rather than going into your target. We don't think in the near term, we have to run power levels above 250 watts per square meter. That's a nice, safe power level to get it down onto the ground. The studies starting in the 70s looked at that as a limit. So we think that's about where there's going to be kind of a global consensus on nobody does anything above that. All right, and how much time do I have left here? 1 minute. Okay, so we've actually tested hardware. So this is Rectenna Performance. It's not a well-known technology, but this is an antenna and a diode connected together. It lets us get the power converted very efficiently. And we put all this together. The area you see recent space-based solar power estimates. That's from Fraser Nash, Roland Berger. These guys have all looked at it, done government-paid studies, and said, hey, space-based solar can come in where you see that general area. It's competitive with the other sources we have, and there's spaces that's going to make sense. We think we can even do better than that. And at the end of the day, space-based solar power is a scalable technology. It can power civilization. It's firm, clean, and renewable. It's good for all times, all seasons, all weather, and all latitudes. Very, very critical. And what it means is more power, less land, less resources, and less costs. That's it. So, thank you.
That was wonderful. Thank you. We are actually out of time, but okay, Sarah, real quick.
You said we can't launch anything right now that's about like 10 meters across. So, like, what's the timeline that you expect to achieve the $5 a kilowatt hour?
We're looking at into this decade for being able to turn a commercial system on. And I didn't say we can't launch. I mean, we're launching system. The plan is to launch something that's about a meter and a half across, and then have assembly in orbit where those are built into larger grids. So we have one basic part number, produce it in high volumes, connect it together into an array, and then turn it on and beam power down. We've actually got a first customer lined up. So if we demonstrate we can make it work, they'll buy the energy. So there are folks that are looking at if they can get 24/7 green power, it has a lot of benefit, and getting it cheaper than a battery buffered system gives them a lot of advantages.
All right. Thank you again. And really appreciate the demo. That was very impressive.